Chapter 12, Part B: Deflection of beams and shafts based on moment area theorem. Example 1. In this example, we are going to solve a deflection, maximum deflection, and also the theta at the free end. So that's a cantilever beam of A and B with the length of L, handling a concentrated load of P at the free end. So we want to know what is the maximum deflection at B and what is the theta at B at the free end, because theta at A is a fixed, there is no delta, there is no theta. So a solution one, a drawing method. So if we draw the shear moment and M over EI, after M over EI, area under M over EI is theta. If you remember, integration over M over EI is theta, and area under theta is the delta. So let's see how that goes. So if this is our force, moment area under M over EI would be y second, and that's a PL over EI, because the moment created here is PL divided by EI is PL over EI. And then from a moment M over EI, if you calculate the area under M over EI, you will get the theta. So that's a second degree. This is a linear. So theta goes by a 1 degree higher than moment. So that's a second degree. And area under M over EI is just something like the first the area under M over EI, area under this triangle. It just gives us a numeric value for the theta. So that's nothing but a PL over EI times L times 1 over 2 because of triangle. So that's PL squared over 2 EI. And that's Y prime or theta. And then if you just go a step farther, this is second degree, delta goes by 1 degree higher, and that's a third degree. And the area under theta is a the amount of delta maximum at B. And if you remember, if we if we have a parabolic spandrel like this by second degree, that's a 1/3 the area, B times H. So the rest of area is 2/3 of BH. And RB is length of the beam, and H is the PL squared over 2EI. So if that's 2/3 of L times 1 of M, cancel with this one, and that's PL cubed. A Yep. That's a 2/3 of PL, 2/3 of PL squared over 2EI, 2/3 of PL squared over 2EI times the length. So that's a PL cubed over 3EI. So uh, one can say the maximum deflection is PL cubed over 3EI, and theta is PL squared over 2EI. Let's solve it with a different method. So that was a drawing, from drawing shear moment. So we start from the moment. We then draw the shear and just go to theta and delta. And at the same time, you can solve it with a just drawing the moment. and m over ei. mm, and this time find the centroid, and that's m over ei, that's bisegunt. And this time, and again, this is a 2/3 of L. If that's the centroid, that's 1/3 of L. This is 2/3 of L. Solution 2 is based on moment area method. So one can easily say, if you can say this is T of B with respect A, and tangent of B with respect to A. So that's a, if you draw a tangent from A, mhm, so it just gives you a T tangent of B with respect to A, and that's a area under moment A from the vertical line of B. So that's a 2/3 of L centroid 2 times 2/3 of L. So if you do the mass T with respect to the T tangent of B with respect to A is equal to, you can easily see that's the amount of, so if you draw a tangent from A, which intercept a vertical line from B, it just simply give you the maximum deflection. So that's a TB with respect to A, and that's a half of area of a triangle, a half of PL over EI times L times 2/3 of L. And if you do the math, it gives you the same numeric value of PL cubed over a 3EI. And theta of B, it's just simply area under M over EI, and that's a half of PL over EI times L. That's PL squared over 2EI, which we already have. You can also solve this problem with a Castigliano's method, which is in chapter 12 of chapter 14, energy method. So how that goes, that says if you know the calculate the moment, and that moment is ma is p times x, force times the length of a section somewhere here, and u is a integration from 0 to L a m squared, which is p squared times x squared over 2ei dx, and that gives you uh, p squared L cubed over 6ei, and that's equal to a half of p times delta b is equal to u. If you, that's a half of the area, that's a half of p times delta b is equal to the energy. So in that sense, delta b is equal to p L cubed over 3ei. That's a three approaches that you can solve a cantilever beam happen to handle a concentrated load at free end. We will solve a more examples. Just give me some feedback on the video. Thank you.